Okay, let's do another example here where this time we're going to look at the difference explicitly between the empirical formula and the molecular formula of this compound. So this time we have two pieces of information. We have the weights, the ratio of the weights of the elements that make up the compound, again by mass. Okay, so that's this information. But we also know that the molecular weight should be 176 atomic mass units. And we're going to see how this information will influence us taking an empirical formula. We're going to get an empirical and translate it into a molecular formula. So first, let's work out the empirical formula. That is just the ratios of the atoms themselves by number, not by mass, but by number. In other words, the number of moles of each. So same process here. Let's pretend we have 100 grams of this unknown substance. And if we break it up, then it would be 40.9 grams carbon, 4.5 grams hydrogen, and 54.6 grams oxygen. So then finding the number of moles of these, the number of moles of carbon would be 40.9 grams times 1 over the molar mass of carbon. And rather than going down to the periodic table again, I'm just going to tell you that this is 12.0 grams. That's the molar mass of carbon. Okay, carbon. And this comes out to be about 3.41 moles of carbon. And again, we'll hold on to that. Then let's do hydrogen, where we're going to have 4.5 grams of the hydrogen multiplied by 1 over the molar mass, which is basically 1.01 grams. Hydrogen just has a proton. This is going to come out to about 4.5. So it may surprise you, or it may not surprise you, that even though carbon by weight makes up the massive bulk compared to hydrogen at least, but not compared to oxygen, there's much more by weight carbon, even though there's more moles of hydrogen. And the way that this is possible is because the molar mass of carbon is so much greater than the molar mass of hydrogen. So more by mass does not mean more by mole. And finally, oxygen with 54.6 grams and a molar mass of essentially 16. This comes out to 3.41 moles of oxygen. So something about this example is these are not particularly nice numbers to work with. We can see that carbon and oxygen have a 1-to-1 ratio, but it's not entirely obvious what the ratio is between the hydrogen and either of those two things. So we can try to make some headway by doing a little bit of numerology and taking the ratio of the largest one. So let's take like hydrogen to, say, carbon and see what we get. So 4.5 to 3.41. And this is about 1.01 1.33. So if I was going to try to write a ratio then between all three of these things, between carbon, hydrogen, and oxygen, I could say we have a ratio of approximately 1 to 1.33 to 1. The problem is, even for an empirical formula, you want to have whole numbers, the smallest combination of whole numbers possible. And we don't have that right now. We have a number that does not look close enough to 1 or to 2 to be rounded to either. But that 0.33 makes me think of something. It makes me think of something from math where you may have seen that 1/3 is equal to 0.333333333, continuing onwards. So when you see something like this, you can think, oh, well, maybe I can rationalize this number, meaning maybe I can turn this number, this 1.33, into a whole number, or sorry, a ratio of whole numbers. And we can indeed do this. Okay, let me get rid of this. So we can write 1.33 as a mixed number, say 1 and 1/3, which we could then write as 4/3. Now our ratio looks a little bit nicer, 1 to 4/3 to 1. Now, if you can get your ratio to look like this, well, we could just multiply everything by 3. Kind of like finding a lowest common denominator. So if we do that, what would we get? If we multiplied all of them by 3, we would get 3 to 4 to 3. Okay. And again, these were for carbon, hydrogen, and oxygen. Okay. So we have our ratios, which then would imply to us, if we wanted to turn this into an empirical formula, we should have C3H4O3. And this is our empirical formula. So if our problem was strictly to find the empirical formula, then we're done. But there's a little bit more that we need to do because we have an extra piece of information. If we go back to the beginning, Dr. Scully told us, additionally, that the known molecular weight of whatever this compound is 176 AMU. Okay, so let's go down here and see what the molecular weight of our compound is with our empirical formula. Just like we've done many times, we just add them up. So the molecular weight of whatever this thing is, our C3H4O3, that's going to be 3 times the molecular weight of oxygen, or sorry, of carbon, which is 12, plus 4 times that of hydrogen, which is about 1, plus 3 times that of oxygen, which is about 16. I'm being a little bit quick with the rounding here, but that's okay. And again, this is going to be AMU. And so what does this work out to be if I plug this in a calculator? Plus 3 times 16. So this turns out to be 88 AMU. This is for the empirical formula that we got. This is the empirical formulas, molar mass. But we know that this substance actually should have 176 AMU. 176. So we know we need this to be 176 AMU. Well, what this might mean is that even though our ratios of 3 to 4 to 3 is correct, we may need to multiply all of those by some whole number. Well, what if we divide the known molecular weight by the empirical one? What would we get? Let's see, 176 divided by 88. Well, that is exactly 2. So what this implies is that our empirical formula, though it has the correct ratios of carbon, hydrogen, and oxygen, does not have the amounts that strictly match the molecular formula. So what we need to do, because the known atomic weight, or the known molecular weight, is twice that of what we found, we need to double everything. So we really want to have C6, H8, O6. And that brings us to the correct molecular formula for ascorbic acid. And this example then demonstrates the connection between an empirical formula and molecular formula.